Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Well, it's my pleasure to welcome Mona Ataria here. Mona is getting her PhD at the University of Michigan, working under Jason Flynn. And many of you probably know Mona already from her recent internship here. So I'll let Mona go ahead and start her talk and tell us about troubleshooting and information flow.
Okay, thank you very much. It's a pleasure to be here. It's great to see all these familiar faces. So today I'm going to talk about software configuration troubleshooting, and I'm going to tell you how we use dynamic information flow analysis to improve this problem. So software systems are very complex. I want my software to run faster, to give me more features, and most importantly, I want to be able to personalize my software. So we're constantly pushing our software to be faster and bigger and better, and that has made our software fundamentally complex. So now the problem is that when something goes wrong, the troubleshooting becomes very difficult. So the troubleshooting, it's very time-consuming, it's very tedious, it usually requires a lot of expertise, and it's also very costly to corporations. So let's see what causes software to have problems in the first place. So here, I show you in a study that was published in 1985. It's a classic study by Gray. And he looked at the outages of, the root causes of outages in a commercial system. So I want to draw your attention to this big red part. About 42% of the outages were due to administration problems. And that's basically configuration and maintenance. So 26 years later, this is another study that was published just last year, SOSP 2011. And again, so they looked at the root causes of severe problems reported by the customers of a company that provides the storage systems. And again, you can see that the biggest root cause is configuration, about 31%. So there's many other studies during these years that actually suggest the same idea, that misconfigurations are the dominant cause of problems in deployed systems. And these are severe problems. These are problems that lead to performance degradation. They leave your system to be partially or fully unavailable. Let me give you two more stories on the impact of misconfiguration problems. Facebook went down, a couple years ago, went down for about 2.5 hours. And it wasn't reachable to millions of users. So many people didn't know how to waste their time anymore. And the problem turned out to be an incorrect configuration value that got propagated. Another story. The entire .se domain for country Sweden went down for about 1 hour. It affected thousands of hosts and millions of users. And the problem turned out to be a DNS misconfiguration. So these kind of problems happen a lot in software systems. And when they happen, they're very difficult to fix. And as I mentioned, they're also very costly. So reports show that, for instance, technical support contributes about 17% of the total cost of ownership for today's desktop computers. The majority of that is just troubleshooting configuration problem. And there are many other studies that suggest the same result. So in the past couple of years, I've been focusing on the problem of improving configuration troubleshooting. I've worked on several different projects, and I've developed several different tools. I worked on a project called Autobash. It was published at SOSP 07, and it basically provides a set of tools to the users to help them fix their configuration problems more easily. I developed a tool called CConf that diagnoses misconfigurations using a bug database. And my most recent tools are ConfAid and X-Ray, and they both diagnose misconfigurations that come from configuration files. ConfAid does that for misconfigurations that lead to failures and incorrect output, and X-Ray does that for performance misconfigurations. And I'm going to talk about these two today. All right. So the goal of my research is to help two types of users. First is end users, who might just be having a problem with their, an application on their personal computer. And the second is the administrators who might be in charge of maintaining a large system. None of these users are necessarily have access to the source code of the application. Or they might just simply not be interested in looking at the source code, or might not have the expertise to look at the source code. So when they have a problem, what happens is that they usually try different things that they know, try to fix a problem on their own. And if that doesn't help, the next step is usually to go online, look at the forums, and look at the manuals. and try to see if other people had similar problems. And basically using a trial and error process to just try a bunch of different things that people suggested and see if that helps or that fixes the problem. Otherwise, they'll try something else. I personally find this to be very frustrating and very tedious, and I think this is why people hate computers so much, because when something goes wrong, it's just so difficult to fix it. So, wouldn't it be great if we had a fix it button? And what it does is that when your program is not working, you just say fix it, and it would magically start working. So we're not there yet. I'm not going to give you that. But we can still do much better than we are doing right now. So how about I give you an easy button? And what it does is that when your program is not working, it would give you a list of potential root causes. And what if almost always the first couple of root causes that it gives you are actually accurate and are actually correct? That's exactly what ConfAid and X-ray do. ConfAid gives you this list for misconfigurations that lead to failures, and X-ray does that for misconfigurations that lead to performance problems. Yes?
Is this equivalent to when you type a problem into a search engine and you get a list of root causes?
Yes, but you have to go through it, and most of the time it's, you read this, it's completely incorrect, you try it, your system is even worse than where it was.
This can be incorrect too, right? Or is it have you ranked them statistically, or?
I'll show you how we rank them.
Okay.
It's better than Google result.
Are you going to prove that?
Practically.
Okay.
But the thing is that the problem with searching for a problem like that is that it's all it's all in English. You basically come up with a description of your problem, and then hopefully someone else described the problem the same way that you did, and hopefully it will show up. Most of the time you just read the forum, and at the end nobody really came up with a solution. So it's a lot more difficult in that sense. What we try to do is to give you, okay, this one and this one, go look at these, and these are hopefully your answers. So okay, so let me tell you a little bit about the core idea behind ConfAid and X-ray. Here is our observation. We have a program. It reads from configuration sources. It does something, and then generates an outcome that's incorrect. So the program is like a black box. We don't know how it used the configuration sources to generate the outcome. However, the application itself knows how it got there. So if we open up this black box, and if we analyze how the application is running, yes, go ahead.
In your world, typically programs have other dependencies besides their own configuration. Are you going to take those into account or not?
What do you mean? You mean like the input, or you mean?
I mean things like DLLs on the computer, for instance, or a program using some other libraries, and then those libraries not being compatible. So it's not that program's configuration; it's compatibility issues between programs.
That's a good point. So in general, most of that actually goes under the configuration, the general term of configuration, like using different libraries, maybe. So that is part of the configuration. I don't specifically look at the problem of not, using the wrong DLL or not being compatible. But in general, that falls into the category of configuration. So we usually say, okay, this is the configuration of the system, and this is the actual input of the system. So these are, the main two inputs that go into the system. I look specifically at the configuration of the application, but that's definitely another source of, I'd say, configuration again. Okay, so if we open up this black box and we look at how the application runs, how it uses these sources, and how it uses these sources to generate the outcome, then we might be able to infer which one of these configuration sources are causing the outcome to be incorrect. So basically, if we analyze the program as it runs, then we might be able to infer what's going on. So that's the main idea behind both ConfAid and X-ray. Okay, so this is the outline of my talk. I'm going to first talk about ConfAid. I'm going to give you some details on the algorithms that we use to do the analysis that I just described. And I'm going to talk about some of the heuristics that we use to make it more practical. And then I'm going to switch gears and talk about X-ray. And then I'll spend some time and talk about the research directions I'd like to pursue in the future, and I'll conclude. All right. So So let's say we have an application. It reads something from a configuration file, it runs for a while, and an error happens. We'd like to know what parameter in the configuration file is causing the error to happen at the end. So let's take a look at this very simple code. The application reads a token. The token is equal to execCGI, for instance, in this case. Therefore, the variable executCGI is going to be set to 1. Later on, because the variable executCGI is equal to 1, the error happens. So as you can see, there are causal relationships in the execution that basically connects the execCGI variable to the error that's happening at the end. And ConfAid is basically interested in these kind of causal relationships. And we use taint tracking, which is a common technique that's used in security, to find these causal relationships. So here's what we do. Whenever a token, for instance, here execCGI, is read into the application, we assign a specific taint or mark to that. And then as the application runs, we use data flow and control flow to propagate this taint. And when we get to the error, we can use this taint to link it back to the configuration token that caused it. So the goal here is to avoid the error that we are seeing at the end and also not lead to new errors. So the goal is to find a successful path. So here is a simple example. We have an application. It has 3 if conditionals. Each of them is dependent on a configuration parameter. And we have an error that's happening at the end. We would like to know which one of these configuration parameters, blue or red or green, can be the root cause of the problem that we are seeing at the end. So the blue option cannot be the root cause. Because even if you change that, if you manage to get the application to take the other path, it would still merge before the error. So we get to the same error at the end. So it cannot be the root cause. The red option cannot be the root cause either, because if you change it and you get the application to go the other way, you would avoid the original error, but then it would lead to new errors on the other path. So the red option cannot be the root cause either. The green option, however, can potentially be the root cause, because if you change it, you would avoid the original error, and then it seems to be successfully continuing and not leading to new errors. And that's exactly what ConfAid returns. A list of root causes that, if changed, a list of configuration options that, if changed, would avoid the original error and wouldn't themselves lead to new errors. All right. So now I'm going to talk about the algorithms that we use for taint tracking. Yes, please.
Question. You said green might be the root cause, but wouldn't it be like a combination of red plus green that will lead to that path?
Yeah, so this is a very simple case. For instance, let's say, if you have, an option here that's dependent on both of them, of course. But this is a very simple case where we're assuming that this one is only dependent on green. Of course, you can have cases where it's green and red, and we can tell you that. But this is just very simplified.
But you need
case.
the red to go right on that branch, right? In the second conditional.
Yeah.
If it goes left, then you wouldn't trigger it, right?
Yeah. So if it goes, so the idea is that if you change red and it goes left, then it's not good, because you'd see a new problem, and that's not what you want. So if you change red, then you won't see that error that you were seeing, but you see a new error, and that's not good either.
If red has, say, 3 values, and there's a third branch, it doesn't lead to another error.
If it's possible that it doesn't go here, then we consider that. This is the case where we know it would go there. Okay. All right. So, okay, so I'm going to talk about the algorithms that we use for taint tracking now. So before I get to the details, I'm going to talk about why we decided to do taint tracking. So information flow analysis in general can be implemented in multiple different ways. You can do it statically, you can do it dynamically, you can use symbolic execution, just to name a few. Why did we decide to go with taint tracking? So we had several design principles in mind that kind of led us to this decision. First of all, we felt that a practical tool cannot rely on the source code of the application, simply because for many of the applications that we use every day, we don't have the source code. So it has to rely only on the binary. The second point is that a practical tool has to be able to analyze complex applications, because these are the kind of applications that we usually have problems with. So you have to be able to analyze complex data structures, has to support multi-threaded, inter-process communication, and things like that. And the third point is that we need to have a reasonable performance. So the good thing about troubleshooting is that we are competing against a human. So we don't have to be extremely fast. You probably won't mind, waiting a minute or two for the troubleshooting to finish, but you probably do mind waiting 20 hours. You might just as well go and Google, as Ed said, and find the answer. So we need to have reasonable performance. Other implementations of information flow analysis that we had at the time fell short in meeting at least one of these criteria. So we decided to go with taint tracking. And taint tracking, as I mentioned, is actually pretty popular in security. So here I want to suggest that it actually might be a better suit for troubleshooting problem compared to security. And here are a couple of reasons. First of all, our environment is not adversarial. The developer of the application, unlike the hacker, does not have an incentive to bypass our system. At worst, they're going to be agnostic to our system, and at best, they're going to actually write the program in such a way that lends itself better to the type of heuristics that we use. And also, I think that performance is probably less of an issue for us because, again, a couple minutes might be okay for troubleshooting, but if you have to wait a couple minutes every time you want to load a web page, that's probably a problem. So for these reasons, I think taint tracking might be a better fit for our problem compared to security. Security people, if they object, they can. Okay. So let's get to details here. So let me introduce our notation. T of x is a taint set of variable x. And it includes all the configuration tokens that, if changed, the value of x might change. And I used color triangles here to show different configuration tokens. Taint propagates via data flow and control flow. Here's a very simple example of data flow. We have x equal y plus z. The taint set of y is red and blue configuration tokens, and the taint set of z is green and blue. So of course, if any of these tokens change, potentially the value of x might change as well. So the taint set of x is going to have all of them, the union of the two sets. Taint also propagates via control flow. And many of the systems that implement taint tracking actually ignore control flow because it's expensive and it's more difficult. However, we realized that for our purpose, it's actually pretty essential because most of our taint gets propagated via control flow. So here's a simple example. We have a conditional that's tainted, here's C, and we would like to know what could cause the value of x to be different at the end. So of course, the value of x could be different because A is different, and that's via data flow, as I just explained. The value of x could be different because of the value of C. Because if you change C, you might get the program to not run this, and then, therefore, the value of x could be different. There's another subtle way that we could change the value of x, and that's by changing the previous value of x, and at the same time, changing C to make the application to take the else part or this other part. But note that both of these need to change at the same time to give us a different value for x. So let me introduce to you our first heuristic. ConfAid currently does not follow joint root causes. Basically, it won't tell you that these two need to change at the same time. It will tell you that these are both potential root causes, but it won't tell you that you have to change them at the same time. So we're basically not following this final term.
By what you mean, you're just going to, that'll just be a blue triangle?
No, we would just not have that. We would basically say that, okay, either value of x is going to change because of A, or we would change C and the value of x is going to be what it was before. So if the actual root cause is the blue triangle, what you do is that you'll see red and green, you change green, and then you would see blue in the next round, because then you wouldn't run this, and then the blue would show up in the next round. So you might have to run your application multiple times to see all the possible root causes. It really depends on the structure of the program, though. Okay, so there is another subtle way that control flow can propagate taint, and that's via the code that doesn't run. So let's take a look at this example. Here C is tainted, and the application takes the if part. The value of y is technically dependent on the value of C, though, because if the value of C is different, then the application could potentially take the else part, and then that would change the value of y. ConfAid is interested in finding these kind of dependencies as well. However, as I explained, ConfAid does the analysis as the application runs, and the application doesn't do the else part. So how do we find out about these kind of dependencies? So here's what we do. When we run the application, if we see a conditional that's tainted, we take a checkpoint, we flip the conditional, we make the application artificially go the other way, we run it, and we find out about assignments like y equal a we call this the alternate path, on the alternate path. And when it merges, we basically roll back everything that we did, we restore the checkpoint, and we continue. So let me tell you about our second heuristic. We only run the alternate path up to a certain threshold, and that's basically to prevent ConfAid from being stuck in really long alternate paths. So what happens is that ConfAid runs the alternate path. If it hits the maximum number of instructions, it would just say, okay, I couldn't see the merge point, I've run enough, I'm just going to roll back and continue. So this may cause false positives and false negatives, but it has big performance gains for us. So we decided to do this. All right, so usually at this point, people ask, well, how about false positives? Don't get a lot of false positives. Once you see a case where you see that the error is dependent on all configuration options. And the answer is actually yes, we did see something like that. And the problem was that we basically treated all kinds of taints, propagations equally. So data flow was basically equal to control flow. And also we treated taint like a binary value. A variable was either tainted by an option or not tainted by an option. And we realized that that's not actually sufficient. For instance, we saw that the conditionals that are closer to the error are usually much more relevant to the error compared to the conditionals that are very far from the error. And also, we saw that data flow usually introduces a stronger dependency compared to control flow. However, we couldn't capture this with the regular taint analysis. So we introduced our next heuristic, which is we call weighting heuristic. And what it does is that it assigns weights to the taints as they propagate. And these weights are basically numerical values that indicate how ConfAid thinks that taint is strong. So the way that we assign these taints is that the conditional that's closer to error get to propagate a bigger weight compared to the conditional that's farther, and the taint that's coming from a data flow is going to have a bigger weight compared to the one that's coming from a control flow. So now, with these weights, ConfAid is able to actually rank the root cause for you. That's how we get the ranked list. The configuration values that get a higher weight become ranked first, and then it goes from there. So that's how we get the ranked list, yes?
So now that you're at false positives, how do you deal with tainted pointers?
What do you mean, like a tainted pointer, like
so
you follow a tainted?
It's tainted, but not the content is tainted. So there are two ways to deal with this, right? So for some table lookups and stuff, if the index is tainted, then although the content is not tainted, for some applications you treat that the taint should propagate for table lookups. For some other cases, that will cause a lot of false positives, so you don't want to do that. So how do you deal with that?
Currently, we do. If the address is tainted, we take the taint. Currently, that's how we do it.
Take the taint?
We do take the taint. So we basically say that if your address is tainted, whatever you're taking is going to have that taint as well. So for instance, if let's say you are looking at, you're traversing an array and the index is tainted, that's going to taint whatever you read.
Right, but if the base of the table is tainted, right? So the address, right? Then it may cause a lot of false positives, right? For instance,
yes, but if you don't do that,
right?
If you don't do that, it causes false negatives.
Right.
Yeah. So what we did was that we basically felt that okay, if we can deal with the false positive part, we better do that than have a list that does not contain the actual root cause. So we actually had cases where we didn't do that and we saw false negatives. So we just decided to do that. It causes false positives, but the good thing is that if you're doing the weighting, it might just get fade away, and then it just disappears.
Have you seen the case that weight helps to reduce false positives caused by putting this address
The taint from the address?
Right.
So we did it, and then we did the weighting. So I'm not quite sure which one of the cases, if we didn't have the weight, would cause that false positive because of the address. I don't know specifically which one of the cases would be worse. But the weight, if we don't have the weighting, we're going to have a lot of false positives in general. Okay. Okay. So the analysis that I just described is actually pretty expensive. The slowdown is in the order of two orders of magnitude slowdown. So it's actually a pretty expensive analysis. That might be okay for the application. Maybe if you're just running your application on a desktop and every now and then you need to troubleshoot. But it's not okay if you want to troubleshoot maybe a server in a production environment. And also, sometimes the symptoms of the problem are time dependent. So if you are perturbing the timing a lot, you might not see the symptoms again. The symptoms might change. And also, we're kind of relying here on the user to reproduce the problem for us. So you see a problem, now you want to analyze it. You reproduce the problem, and then we would analyze it for you. However, some of the problems, especially performance problems, are really hard to reproduce. You might not be able to right away create it again. To address all of these problems, we decided to develop a very lightweight deterministic record and replay system. And we run the applications all on top of this. This is all in kernel. And deterministic record and replay system, basically, what it does is that when the application is running, it records all the non-deterministic events, for instance, return value of system calls, signals, and all the timing information. And it records all of that in a log. And later, we use this log to recreate the exact same execution. And then we run all the analysis on the replay of the execution. So basically, get rid of all this overhead on the online system. So as I mentioned, we use the log, we replay the execution later, and then we run the heavy analysis on the replay. I'm not going to go into too much details on this system, but the main difference between our system and other deterministic record and replay projects out there is in the fidelity of our replay. So the fidelity of our replay needs to be strict enough to create the same execution as the record. However, because we do analysis in the record, we basically instrument the replay, and then we do the analysis inside, our fidelity should be loose enough to allow this extra code to run within it. And we achieve this via a careful code design. Our replay system is instrumentation aware. It can differentiate between the replay code and the analysis code that we are running. So I'm not going to talk too much about this. I'll be happy to talk to you offline about this if you're interested. All right, so let me show you some results. So we used ConfAid to troubleshoot 3 applications: OpenSSH, Apache Web Server, and Postfix Mail Server. We looked online, looked at the forums and manuals, and found 18 misconfigurations that people reported for these 3 applications. We recreated these, and then we ran them with ConfAid to see if we could find out the correct root cause. And ConfAid was very successful. It could correctly find the correct root cause, rank it first or second in all of these cases. And these are the total number of configuration options that were available in the configuration files. So in 72% of the cases, the correct root cause was ranked first. In 5 cases, it was ranked second, and we never ranked it worse than second. Yes, yeah.
Could you talk a little bit more about the variety? Are these shallow configuration bugs, or some of them deeply nested configuration files? How does that make a difference on the complexity for ConfAid to find the bug?
It does make a difference. I'm going to show you another set of evaluation to right after this. These are mostly very deep configuration problems where people actually tried a couple different things, they couldn't figure out what it was, and they actually, posted in a forum, waited a couple of days. So actually, when you look at it in the code, it's actually pretty deep. It takes a while. I have another a data set that I'm going to show you right after this that creates more shallow cases. And definitely for the shallow ones, it's easier. And the results are actually going to show that as well. And there was another question. Yes.
So, and if a user using ConfAid, how do I specify the failure point?
Oh, that's a very good question. So there are different types of failure. There's some failures that are obvious, like asserts or crash, something like that. There are failures that are not obvious, and we're relying on the user to tell us. For instance, you see a message and you just don't like it. You say, you tell us that this is an error. Or it might not even be like message like that. You might, for instance, run Apache and get a, file from Apache and just tell us that this is wrong. So we basically rely on the user to tell us what is wrong and what is right. Right now, we have a very simple way of doing that. So the user tells us, whenever you're telling me you're printing something with this message on the screen, or you're giving me something with this content over the network, this is wrong.
But it may not be easy to use because you assume user doesn't look at the source code, doesn't know the source code.
Well, you don't really require the source code for that because you only see the outcome. So you have a way of figuring out that something is wrong. So you see a message, you say, okay, this is an error to me. You see, a content that seems wrong to you. So you don't need to know about the source code. You just see what is, the application is printing or giving you. So if you just specify that to us, that would be sufficient.
The issue here is with relying on the user is like multiple root causes might generate the same user visible error. And
sure.
Then how does ConfAid know right from wrong in the ways you're doing things?
So we are looking at that specific execution that caused that message. So of course there could be other ways that could lead to the same problem, but we are analyzing that specific execution that happened. See what I'm saying? So there might be multiple ways to get there. We're not analyzing those. We're only analyzing the actual execution that you saw that led to that error. So we're recreating the error. We're using the record and replay to recreate the exact same error, and we're analyzing that execution path. And then we see which one of the options are affecting that execution path. Does that answer the question?
I think so. I think there's some gaps in understanding, but that's fine. Yeah.
Okay. Yes.
So when you were building the algorithm that prioritizes which configuration settings, what was your training set like? Do you have bugs from these three applications, or were they from different applications?
We did not have bugs from. So we tried OpenSSH first, and then we saw that okay, there are a lot of false positives. Seems that there are a lot of false positives, and then we saw that most of the time the conditional that's closer is relevant, and sometimes we're reporting something that's very far. So we realized that might be something that we should be looking at, and then we added that to the code, and then we ran Apache and Postfix and later Postgres, and they all seem to be they seem to be pretty good.
So you
afterwards.
use these bugs to tune your system?
I use the OpenSSH. So I first did the OpenSSH, and then it ran fine for a couple of the bugs, and then for a couple more, we saw a lot of false positives. And then we decided to fix the false positive problem. And then we introduced the weighting heuristic. But then
So
afterwards,
you're training and testing on the same bugs?
there's not much training. It's just it gave us the idea that maybe we should have a way of specifying which conditionals are more important, which taints are more important. We're not using any statistical method to figure out. We basically have a simple heuristic that says the conditional that's closer is more important.
But you came up with a heuristic based on these bugs.
Based on the OpenSSH bugs.
Okay.
Yes. And then we used that, and we ran Apache and Postfix, and they both ran great. And then we ran the other set that I'm going to show you after this, and they ran great.
So you didn't change your heuristics at all
Afterwards,
after OpenSSH?
No.
You didn't touch anything after Apache or Postfix?
And then we also did X-ray, and that was fine too.
Okay.
So if I have a bug that shows up because I set the Windows permissions wrong on a share, therefore INS isn't going to read it, which has happened to me. Does that show up as a token here, as a system call failure, or how does that show up in your system?
Windows permissions. Is it kind of, something close maybe to Unix file permissions?
Yeah, just think of create files or
Sure.
sort of fopen failed with
Sure.
a particular error code.
So here I'm looking at the parameters in the configuration file. So it won't show as a parameter that I'm looking at, but this technique can be extended to also follow those kind of configuration values as well. So it can be easily extended to extending it to also follow.
Log the entire state of my Windows machine because the permissions check is in the kernel. It's not in my IIS process.
All right, let me try to understand this. So you're trying to read something, and it says that you don't have the permission, right? That's pretty much enough for us because we say that okay, permission here. So for instance, for Unix, you perform a system call. It gives you a code that says permission denied, something like that. So we just use that and say, okay, permission was wrong for this file. So we don't really need to go into kernel and see how exactly it does it, but then we just use the result.
I guess the point is you don't have the information flow
In the
tracked
kernel.
from the actual permission setting on the slide through to the failure of the call.
No,
Right.
we have it. We just see the end of it that says, okay, you don't have permission. We certainly don't follow kernel as well. When we have a system call, we don't go into the kernel.
Thank you.
Andrew or
So the output of this analysis is the name of the configuration variable that is incorrect. But do you know what the right value is, or do you know how to fix the problem?
we don't. So we basically tell you that these are the options that most likely causing your problem. We don't tell you how to fix it.
So is it easy in these cases? Like, was it easy to fix the problem once?
So here's the thing. Here's why we don't tell you how to fix it. Sometimes changing that option is not necessarily the right fix. For instance, you see that, okay, I can't access this because of authentication problem. You don't want to remove authentication. You don't want to change authentication, right? So it basically suggests the user that this is causing your problem. It's up to the user to decide whether they want to add something, whether they want to change the value. Of course, you can change it and run the tool again to see if there are any new root causes. But we don't necessarily make that decision of whether you should change it or not. Andrew.
I guess another way of restating this sort of issue that David raised is that potentially the configuration of the system is not just the configuration file, but the permissions on every file and the machine and all the libraries. And
That's correct.
How does this scale when the size of the configuration set
That's a very good question.
tends to be huge?
That's a very good question. Configuration in general is actually pretty fuzzy, and it can be a lot of things. As I mentioned earlier, your libraries, any file, maybe in your system, the variables, your environment variables, all of these are considered to be configuration. And also, configuration file itself can be maybe extremely huge. We didn't really try. What we tried was like in order of 100 configuration tokens, but I can imagine systems that might have thousands. How does it scale? I can't tell you for sure because I didn't do it, but there is overhead in terms of the amount of memory that we use, first of all, and also as you're running GitVR, the way that we're doing it, we're copying taint for these configuration options over and over in memory. So as your state gets larger and larger, you need to do more when you're doing the analysis. Does that make sense?
Yeah, well, I guess my concern is that if everything in the system is configuration, which it potentially is, then everything ends up getting tainted.
So your application, everything in the system can be configuration, but your application might not read everything in the system, right?
Everything the application reads is sort of, all of the external inputs to your application are potential sources of configuration.
Sure, so your application might start with reading a lot of things from the system. The good thing is that it doesn't use all of that to go down a certain path. It might use all of that to go down all the paths in its lifetime, but you're only looking at one single execution path. And it doesn't use all of that for making decisions for one single execution path. That's the good thing about our system is that when we're writing the code, we're not using all of these little pieces. It's actually, there are actually studies that shows that usually there's only one or two options that are causing a problem. It's not like 10 million different options that are causing your problem.
Follow-up question. So how big is your sort of taint tag? So it's like 8 bits or 16 bits or 32 bits?
So right now we have 1 byte per configuration options that we are tracking. And so it gets a little bit too much details. But the way that we do it is that that shows us the weight. So we have that. So we have that much maximum of that much weight. So each configuration option gets a byte, and if you increase the number of configuration options for each variable, this is going to increase. But each configuration option gets 1 byte. So a variable is going to, if you have 50 different configuration options, a variable is going to have 50 bytes, 1 each for each configuration option.
Some kind of shadow memory that keeps it a taint map, or how do you know
yes.
it's such big?
Yes. So the good thing is that not all your memory becomes dependent on configuration options. So for instance, we run Apache, and at the end, maybe like 70K of it was dependent on configuration options. So there's a big overhead in terms of what we keep, but the good thing is that not all of your memory needs to have that much overhead. So now I can imagine cases where all of a sudden you have giant pieces of memory become dependent on a lot of taint. So we need to we haven't seen that case yet, but what we need to do is to kind of maybe get rid of some of this taint, maybe make it smaller, fade away some of the taint, basically kind of compromise to be able to keep more. But there's a memory overhead.
Do you have a lookup table for each variable that brings you to this taint?
Yes. It's a tree-level lookup table, kind of like a page table type of structure. Yes.
Do you use emulation or binary instrumentation to run your taint analysis? Out of curiosity.
We do it dynamically, if that's what you mean. We use binary instrumentation, and we add all the analysis as the binary runs. Yes.
So it feels like this is could be very useful for the developers. Then potentially another approach is to use, I don't know whether you know about the Sage project, use this kind of approach to do fuzzing and to maybe focus on the configuration errors. And then maybe those errors can be identified at the development time.
Definitely. It can definitely be useful for developers, although we try to we try to not use the source code, so it's also useful for end users and others. But if you have the source code, it's actually going to be much easier. So it can also be used by developers as well. Yes.
And so I was curious about the need to execute multiple times. So if there are dependencies, you said you were going to maybe change some parameters and execute.
So let's say you have a problem where you need to change two things to get it fixed. Depending on the structure of the application, we might give you both of them. It really depends on how the application checks for them. We might give you both of them, like first and second, and then you fix the first one. We don't tell you have to change them at the same time. So you fix the first one, it doesn't go away, you run again, and then you see the second one coming up, and you fix the second one. There are cases where we might miss the second one. And you see the first one, you change that, you run again, and then you see the second one. So we may or may not show you all configuration. It really depends on how the application checks for this. So if, for instance, if you change this and now you go to the alternate path, when we were exploring the alternate path, we maybe aborted early, we didn't see the second one, then we might miss it like that.
So I wonder if you're going to sort of allow sort of multiple runs in your experiment and observe the outcomes, then there are other approaches. So you can, and it's sort of analogous to Sage, but you don't need symbolic execution. I mean, you have your input file or your configuration file, and you have a hypothesis that some byte is the cause. So you change that to some other value, and then you run again, and you observe. And you can do things like code coverage or path profiling, things that are very cheap approximations to taint. Right? So instead of tracking taint, what you say is, most likely if I change this one byte and I look at the code coverage before and after, the differences in the code coverage are only if everything else is deterministic, right? Then if that's the only change I've made, then if I see these differences in the code coverage, those are likely very related to the change.
So I think that approach works very well for fuzzing and testing, because you change something and then you see it. Here we don't know what to change necessarily. You have 100 different options. Which one are you going to change? That's a problem here. What we are trying to give you is that we tell you, okay, these three maybe are the most important ones. So now if you want to go use something like that, like change them a little bit and see how it goes, then it narrows down what you need to look at a whole lot simply by...
I see. So you're saying it's sort of a complementary...
Yeah. Once you do that, then you might be able... So let's say you want to fix your problem. You see that, okay, this option is my problem. You want to automatically fix it. Now maybe you can go change it, bit by bit and see where it goes. Yes.
I have a follow-up question. So if you know, since you know the kind of the failure point, right? Well, have you done kind of backward slicing to see what options are in that code and see whether your thing is can narrow that much farther than just simple backward slicing?
So we didn't do backward slicing. The main reason is that backward slicing for really long execution path is not very successful. So here we have cases where usually it happens that you read the configuration at the very beginning, you run a long path, sometimes you go through processes, and then you get to the error. For postfix, for example, there are 5 processes before you get to the error. So the configuration is in this process, the error is in other process. Backward slicing cannot really go that far, and it kind of has problem going up for really long executions. So that's one of the reasons that we decided to not do program slicing in the first place.
Yeah, I'm just going to propose that slide 24 is very interesting. I should move forward and see what 25 and beyond propose. That's my question statement.
Why do you think it gets better?
So yeah, we're looking forward to
Just something new.
Okay. So this is the other evaluation. Yes. That James wanted to see.
Yeah.
So so we use the tool. It's called ConfAid. It's developed at EPFL, and what it does is that it randomly generates bugs in configuration files that looks like human errors. Why do you laugh, Andrew?
Do you need a tool for that?
It develops a tool. It's actually pretty good for testing. If you want to see your application, if it fails horribly, if a configuration value is wrong, or if it dies gracefully, that's the tool that you use. So it was very useful for us because then we generated 60 bugs using it, and we didn't change any of our heuristics, as Stuart asked. And we ran ConfAid again, and in 55 cases, ConfAid was able to rank the correct root cause first or second. So again, 85% it was actually ranked first, and 7% was ranked second, and there were 5 cases where we didn't rank well, worse than second. So 3 cases, yes, Ed. In 3 cases, in postfix, the correct root cause was a missing configuration option. And that's something that ConfAid doesn't currently support. So you had to add a new configuration option to fix the problem. So that was the 3 postfix ones. The Apache ones, the correct configuration option was ranked 9th. And that was the direct result of our rating heuristic. And the OpenSSH one didn't finish. We needed some more support from one of our system calls, so it didn't complete. Yes?
I have lunch with you. I'll just wait and talk to you.
So quickly, I'm going to show you some performance results. For the real-world bugs, the average time is 1 minute and 32 seconds for the troubleshooting to finish. Again, I want to emphasize that this runs on the replay execution and not online. And for the randomly generated ones, it took 23 seconds. Going back to Ed's question, these turned out to be shallower bugs. For instance, you had a configuration option that only accepted 1 to 10, and you gave it 12. Of course, right away it failed. There were ones that were kind of deeper, but usually they were kind of easier. The real-world bugs turn out to be much harder. All right. Okay, so kind of final note on ConfAid. People usually ask, so why ConfAid is successful? And here is my thought on it. So usually the configuration problems that we see, usually once you find the root cause, it's kind of obvious. Most of the time there is 1 or 2 configuration options that are causing the problem. And of course you can have a case where you have 20 different configuration options causing a problem, but that's very rare. There are actually studies that were published that actually support this, that usually 1 or 2 configuration options are causing a problem. So yes?
This seems like a big claim. I wonder if you actually talk to, administrators or something to actually show the output of ConfAid, and then they could actually go and fix it immediately?
So you're asking whether it's the answers are correct, or whether the 1 or 2 configuration option problem is...
The output is useful.
Okay. So I think the way that we evaluated whether the output is useful or not is just by looking at whether it was the correct configuration option that was causing the problem. Whether you go and change it and then that would fix the problem is a different question, I think. So we recreated the problems and we saw that, okay, this is telling me that this is your root cause and this is the correct root cause that's telling me. We actually used it a couple of times for our problems as well. So we found it useful. We didn't ask any administrators to use it though. The problem mostly was they didn't want to run our deterministic recorder replay in their kernel. So we need to convince them to do that. But I think it is useful. We found it in all the cases that we tried, we found it to be able to narrow down the options a lot. We found that very useful.
I think the output, I mean, having done some diagnostic work, it's like, so the output appears very different to somebody who's building the tool, to somebody who's writing that program versus somebody who's just managing and running that program.
Correct.
So it'll be kind of interesting to see if you take this output to admins and show them the symptoms and the output, see if they actually can fix it.
We actually feel that our tool is probably most useful for people who may not have written the code, may not be familiar with the code, and they're just using it. Because what it gives you is a very general, like is a very high-level result. It's not going to tell you that variable X. It's going to tell you that this configuration option that you actually have access to and you can change.
There's a missing part in that argument where you haven't closed the loop.
Whether it's useful
Yeah, you have a tool for admins.
Definitely. I mean, it's a any system. If you can give it to people, if they come back and tell you that we used it, it was great. Of course, it's going to be awesome. We unfortunately didn't have the time to do that. We felt that within our group we used it and found it interesting. We are making it available, actually, the source code, and it would be interesting to see if people find it useful as well.
I have a comment. I think user mode, the program user runs on desktop is more complicated usually than the server program, like OpenSSH. And when they have, particularly on Windows, right? If I just open the program, there's a large number of registry being accessed, and many files being opened, and they involve many DLLs.
You think Word is more complicated than SQL Server?
In the example she evaluated all the OpenSSH, the three.
Well, have you seen postfix? So I believe that there are many applications on desktop.
So let me reformulate my question. How large is the taint source?
How large is the taint source? How big is the configuration file? In order of hundreds of configuration tokens.
100. I mean, try open a user level program. Look at how many registry they read.
Sure. I don't think that necessarily is gonna translate into bad results. Of course, if you have much larger set, it might it certainly affects the performance. It would be interesting to see if it's gonna result in like worse output too. I don't necessarily think that it translates directly into worse results or more false positives. I do believe that some of the server applications are pretty complex. Postfix is a nightmare. We also did Postgres, which is a database. That also was pretty complex too. So we didn't just try simple applications. All right, yes?
There's actually a nice little industry around outsourcing IT, hiring someone to come help fix your computer over the web. Just thinking we might want you to be able to look at this in that context and say, you've got an expert, and he's got to go through 100 computers today. Maybe this can cut down the time to a call.
Sure. Very interesting. Cool. All right, so just to finish my thought here, finding a root cause is basically like finding a needle in a haystack. There's a lot of work that you need to do, but once you find it, it's obvious. And the good news is that computers are actually good at finding needles in haystacks, and I think that's why ConfAid turned out to be so successful. All right, so moving on quickly, I'm going to talk about X-ray. So far, I talked about configuration problems that lead to incorrect output. And there is another big category of configuration problems that cause performance issues and don't necessarily cause incorrect outcomes. And X-ray deals with those kind of misconfigurations. So what do you do when you have a performance problem? usually people use monitoring tools, profilers, tracing, logging, to see what's going on in the system. The problem with all of these tools is that they tell you what events are happening in your system. What you really want to know is that why those events are happening in your system. So now you need to manually infer why, and that's the part that needs a lot of expertise. So wouldn't it be great if you could automatically infer why as well? Wouldn't it be even greater if you could have a list of root causes? I see smiles. And that's exactly what X-ray tries to do. So X-ray currently analyzes latency, CPU, disk, and network. You can use X-ray to analyze at the granularity of one single request, for instance, for applications like servers that handle requests, or you can analyze over a time interval. And X-ray also gives you this powerful tool where you can analyze 2 or multiple different requests that you think they should have similar performance, but they don't. So here are a bunch of questions that you can ask X-ray. For instance, you can say, I have the server, why is this request being handled so slowly? Or why is CPU usage so high over this time interval? Or I have these 2 different requests, I think they should be similar, why are they different? So let's talk about the idea of X-ray. So we call it performance summarization. So at ConfAid, as I explained, we were basically interested in finding out why a certain piece of code, for instance an error, ran. This bad red block of code. Why did that run? In X-ray, the problem is that we don't know where this red block is. But nothing really prevents us from treating the entire code like red blocks of code and determining why all events in the code ran. That's exactly what we do. So from a really high level, this is how X-ray works. We assign a cost, basically a performance cost, to different events of the execution. Those are instructions and system calls. And then we determine, using a ConfAid-like analysis, why each of those ran. And then we associate this performance cost to the root causes of that we just determined, and then we aggregate over the entire execution, and then we rank the results. So I'm going to use one of the examples that I told you in the last slide. I'm going to walk you through X-ray and tell you how exactly it works. So let's say you have a server, it's handling requests, and one of the requests is particularly slow. We want to know why. So first step, as I mentioned, X-ray analyzes execution, but here we are interested in the execution that's related to that single request, not the entire execution. And that is not always straightforward. Sometimes you have applications that use multiple processes to handle a request. The request comes in, it runs for a while in one process, it then goes to another process, and it continues. We are basically interested in all these blue pieces. All of these are relevant to our request. That's exactly what X-ray does. As the request travels between processes, it collects all these executions that are relevant, and then once it's done, it basically says, okay, these are all of the execution pieces within all of these processes that I care about. So once we have that, then we do the cost assignment. As I mentioned, we assign the cost to the events, and events are instructions and system calls. Here we want to see why a certain request is slow, so we want to look at the latency. And the latency is basically, for system calls, is execution time of the system call that we collect online as part of the record. And for the instructions, we approximate the execution time of each instruction, and we assign it to that instruction. Yes, Andrew?
So if I make a system call and it takes a really long time because the OS is context switched and runs somebody else, how does that play into this cost analysis?
Good point. If you analyze that single request, it might be misleading because that single request wasn't running, it was just sitting. So what you want to do is to look at a time interval, because that would include other processes that were actually running at the same time. So here's the point. We give you a bunch of different tools, and then you can, you're running this on replay, so you can do it multiple times with different types of analysis. You can analyze a request, you can analyze over a time interval, you can do different things to figure out what's going on in the system. This is something that we kind of rely on you as the admin to figure out, to basically use the tools the best you can do. Okay, and yes, so the timings are all collected online, so the analysis is not going to perturb the timings. And then once we have the cost. So for instance, let's say we had like a small block of code, we assign 10 microseconds maybe to it, and then we have a long block of code, maybe it has a really long system call, and it took the cost of 100 microseconds. Then we determine why each of those ran. For instance, very simple case, maybe the first one ran because of configuration option A, the second one ran because of B. We assign the cost to the root causes, and then we aggregate over the entire execution, and we rank. What does this mean? This tells us that X-ray thinks that B is a bigger contributor to the performance of the problem compared to A. So if you're the admin, you want to see why it was slow, go look at B, because that's causing a larger performance cost for you. And then go look at A. So maybe you can't remove B, but this tells you why it was happening. Okay. So as I mentioned, X-ray also gives you this powerful tool where you can compare two different requests and see why the performance of these two requests are different from each other. We call it differential performance summarization. And here's how it works. So you have two requests. We extract the execution pieces of both of them, the way that I mentioned, and then we compare them and find the points where the execution diverges. We call them divergence points. And then what we do is that we calculate the cost for each part of this execution, and the difference is the cost of the divergence point. And then we basically do the same thing. We find out why that divergence point happens. So if it's like, I don't know, maybe if conditional, one of them took the if part, one of them took the else part, and that is the difference between the cost. We assign the cost to the root cause, and then we do that for all the divergence points. Finally, we give you the list. It tells you that A is the biggest contributor to the divergence between the two requests. Not necessarily the performance of each one, but the divergence between the two. So now you might ask, okay, I have thousands of requests. How do I know which two? It's a hard thing to do. So we decided to do that for multiple requests as well. So you can tell us that, okay, I have 100 requests. Tell me why these are having different performances, what is causing different performances, and what is the cost. So what we do is that we kind of compare all of them. We find the shortest path from the beginning to the end, and note that the shortest path is not necessarily a single request. It can be a combination of some of the requests. And then we find all the divergences from the shortest path. We determine the cost. We determine the root causes. And we basically give you a visual, kind of explanation of these are the divergence points, these are the costs. Yes?
Points. Are you assuming implicitly those all depend on control flow? Because you had if B previously on the slide.
Good point. Give me what do you have in mind?
Here's a request that comes in to open a file. File name A, you feed that to fopen, it's in RAM. File name B, you feed that to fopen, it's in Iron Mountain in Utah.
Yeah. So there are cases, especially when you go to the system call part, where because we don't follow that part, where the input to the system call can cause divergences outside that. That we currently don't follow, but we should. We have that in the future kind of direction. But because we don't follow, if we were following the kernel, then we would see that eventually as a divergence in control.
Well, there could be, like network is congested, right? That's why it's taking longer. Would you capture that in any way?
We are trying to look at the configuration reasons. Of course, you can have, my disk is slow because my disk is broken, or my network is slow. So what we are kind of expecting here is that you as the admin kind of look at different potential problems. My hardware not being correct, my network being slow, or I'm having a configuration problem. The good thing is that finding out that, for instance, my hardware is broken or my network is congested for some reason, there are many good tools that allow you to explore that and find out about that. We try to focus on the configuration file where we thought that there are not that many good tools to go with.
Compare, there's a common performance profiling tool is this function being called 20 times, 20% of the time, and another function. And so what's the advantage and the disadvantage of what your tool can provide compared to that kind of performance profiling tool?
That's a great question. Our tool gives you a much higher level idea of what you can do. So if I'm a user, if I'm using an application and you tell me that this function is called a lot of times, I can't do anything. I mean, if I'm not a developer, if I'm not looking at the source code, telling me that this function specifically is like running a lot is not helping me in the overall solution of the problem. What we are trying to give you here is that, okay, this option that you can go and change is causing you trouble. See what I'm saying? So if you're the developer, that might be a good thing because then you can go to that option and then that function and do something. But if you're just using it, giving a very low-level detail of what is going on, it's going to be useless to the user.
I'll wait to see your evaluation to see what's the
sure.
example.
That goes right here.
Right.
So this is actually work in progress. We are still doing some more evaluation, but this is the preliminary result. We did Apache, Postfix, and Postgres. We found 14 test cases of performance problems that people found online and reported. And we recreated them and we ran X-ray. And in 12 cases, the first option that X-ray returned was actually the biggest contributor to the performance problem. And in 2 cases, it was the third option that it returned. Yes, Andrew?
Give me an example of what a test case is.
What they were.
Like the cache isn't big enough? Or?
Sure. Okay, so let me give you an example of maybe the Postgres. So Postgres, for instance, it has a write-ahead log that as it does the transactions, it writes into the log and then it later commits. So now, if you have and then it basically does the snapshots or checkpoints of the log so that if you crash, you can come back. So if your system is under a lot of load and you do a lot of checkpoints, it's going to put even more load on your disk. So the problem that that person described was that I'm having my disk is under a lot of load, and then people suggested that, okay, go look at how frequently you're doing your checkpoints. And the person came back and said, okay, maybe I'm doing checkpoints too often or something like that.
In the case of a thing like that, your tool, you would say, here's one request that went normally, and here's one request that went really slowly because it had to make a checkpoint while it was doing the request?
Okay, so let me first mention, these three, in these 14 cases, we have some of them that we did per request analysis, some of them we did time interval analysis, some of them we did comparison. For the one that I just described, we did a time interval analysis, where we said, okay, we look at this minute to this minute, and then we saw that there's a lot of disk usage, and then we said, okay, the option of checkpoint interval that is in the configuration file of the Postgres is causing a lot of that disk usage. Now we had, for Postfix and Apache, we had cases where we looked at requests specifically. For instance, for Apache, there was this request that was specifically long, and then we figured out that it was doing extra DNS lookups.
How does the user interact with this information? Like if you run
the result, or how does it do the actual analysis?
If you run your tool over a time interval and something's going slow because of a lot of a disk access, what do I as the user give to the system, or what does it give back to me?
So you tell the system, I want to look at disk over this time interval. And the system gives you the list.
Model for this is disk access.
So as a user, you'd say, okay, my disk seems to have a lot of load. My network seems to have a lot of load. So so the thing is that you detect the problem as a user first, and then you tell us what you want to look at. You can, of course, do, okay, over this time interval, tell me about my disk, tell me about my network, tell me about, my latency. You can do that as well. The good thing is that you can run multiple times on the replay, and then you're all fine. But as the user, you need to first detect the problem, and then try to diagnose the problem. The part is that we don't tell you that, okay, your disk is doing bad.
But then you root caused it back to a configuration file.
Yes. Yes. It might be that, your disk is broken, where then, you're not really looking at the configuration problem. But if you are, then it tells you. Okay. Okay. So we have a few minutes. I'm going to talk about some of the future research directions I'd like to pursue. So with software systems becoming more and more complex, the already difficult problem of software reliability and troubleshooting seems to just be getting more challenging. And I believe that software reliability is going to be one of the most important research topics in the future, and I very much like to pursue a couple different directions in this field. More specifically, I like the problem of troubleshooting software that runs in larger scale, and also troubleshooting software that runs on a platform with limited hardware resources. So larger scale analysis. Today we have software that runs on scales larger than ever. We have very complicated distributed systems, and troubleshooting is specifically difficult on these environments. Even before you get to the diagnosis and solution, you need to detect, as I was explaining to the previous question, Andrew, you need to detect that the problem exists. And detecting abnormality is not very straightforward in these cases. Usually, so today it's basically left to the admin, and then how they do it is that they basically look at the logs and try to see if they find any abnormality. And this is really difficult because they keep the log to the minimum. So the question I'd like to answer is it possible to automatically find these kind of abnormalities in the system? And once you find them, maybe you can collect more diagnostic information, and then you can do a better troubleshooting and analysis in the future. I also like to look at troubleshooting for software that runs on a platform that has limited hardware. So mobile computing is greater than ever. We have smart appliances everywhere. These platforms run very complex applications, but they're still very limited in terms of computational resources and in terms of energy and battery life. So when we're designing solutions for troubleshooting for these kind of environments, we should take into consideration all these constraints that they have. So for instance, is it possible to maybe offload some of this troubleshooting to the cloud in a secure and efficient manner so that we're not using that much of the precious resources that we have on the platform? And also for desktop computers. We've done a good job of making our applications more user-friendly, but when it comes to troubleshooting, we still have a long way to go. And for desktop computers, any impact that we have on the troubleshooting is going to be huge, simply because of the number of people who are going to be affected by that. I have a bunch of ideas of what we can do for making troubleshooting easier on desktop computers. I'm going to share with you two of them. The first one is that the configuration state is usually shared. For instance, you have Windows registry, things like that. And when you configure one of the applications, that means that you might be breaking another application. So is it possible to detect proactively that this thing that you're doing is going to break something else? And then let the user know so they're aware of the consequences of the actions that they're taking. Another idea is that, usually when you're configuring something new, a new feature, you might need to change multiple things and modify multiple different things. What people usually do is that they do half of it, and then, there's a problem at the end. Is it possible to automatically figure out what are all the possible configuration options that you need to change at the same time, and then tell the user so they can configure the system correctly to begin with? All right, so conclusion. So problems, unfortunately, are inevitable in complex software systems. I showed you that misconfigurations are the dominant cause of problems in deployed systems these days. And I showed you that execution analysis can greatly improve diagnosis of these kind of problems. I talked about ConfAid and X-ray. They both use dynamic information flow analysis to do this. And I show you that they can be actually pretty successful. And that concludes my talk, and I'd be happy to take more questions.
I think we have time for up to one more question.
Up to one.
All right.